Black holes have a strange way of slipping past our common sense. Even people who are comfortable with science, who understand gravity and stars and galaxies, often feel their intuition falter the moment black holes enter the conversation. Something about them feels different, more extreme, less forgiving. They are not just another object in space. They feel like places where the rules themselves start to hesitate. Part of the reason is language. The words we use already bias our thinking. Hole suggests emptiness, a void, something missing. Black suggests darkness, invisibility, mystery. Together, the phrase almost invites fear. It sounds like a cosmic trapdoor, a place where things disappear and never come back. Popular culture has happily leaned into that imagery, filling movies and books with scenes of stars being swallowed whole, spacecraft stretched like noodles, and portals opening to unknown dimensions. But the real scientific story is both calmer and, in many ways, more unsettling. Hello, and welcome to Sleepy Space Traveler. Today, we are going to explore one of the most mysterious things in the universe, one that has challenged scientists for a long time: black holes. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. Here, we slow everything down. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. And wherever you are, maybe lying in bed, settling into the night, or just looking for a moment of calm. I hope this time feels peaceful. I hope your mind can soften, and this moment can become a pause in your day. Thank you for being here. Now, let's begin. Black holes are not cosmic vacuum cleaners roaming the universe. They do not suck up everything around them indiscriminately. They sit where they form, obeying the same gravitational rules as any other massive object. If the Sun were magically replaced by a black hole of the same mass, Earth would continue orbiting almost exactly as it does now. No dramatic spiraling inward, no sudden doom. And yet, black holes remain deeply strange. They are the only objects in the universe we know of where gravity becomes so intense that our current understanding of physics stops working cleanly. They are places where time and space behave in ways that feel less like smooth extensions of everyday experience and more like abrupt departures from it. And most importantly for our question, they possess a boundary beyond which we cannot see, measure, or receive information. That boundary is what makes people ask, again and again, what's on the other side? At first glance, this seems like a perfectly reasonable question. After all, when we encounter a boundary in everyday life, there is usually something beyond it. On the other side of a wall is another room. On the other side of a mountain is another valley. On the other side of the ocean is another continent. Our brains are trained by experience to expect continuity. Black holes challenge that instinct. In physics, the other side of a black hole is not guaranteed to exist in any meaningful sense. Or if it does, it may not resemble a place, a region, or a destination at all. It may be a breakdown of concepts rather than a hidden location. To understand why, we need to gently strip away the dramatic imagery and rebuild the idea of a black hole from the ground up, using the tools science actually relies on: observation, mathematics, and carefully tested theories. Black holes are not hypothetical anymore. For decades, they were mathematical solutions to Einstein's equations. Strange outcomes that appeared when you pushed gravity to its limits. Many physicists initially assumed they must be unrealistic, artifacts of the math rather than objects nature would allow. But the universe, as it often does, proved more imaginative than we expected. Today, we have overwhelming evidence that black holes are real. We observe stars orbiting invisible massive objects at the centers of galaxies, including our own Milky Way. We detect gravitational waves, ripples in space-time itself, produced when black holes collide and merge. We have even captured images of the shadow cast by a black hole's event horizon, a dark silhouette against glowing plasma. These observations confirm black holes exist, but they do not tell us what lies inside them, and that distinction matters. Science is excellent at describing what we can observe, measure, and test. It becomes much less certain when we ask questions that involve regions of space-time fundamentally cut off from us. The inside of a black hole is not merely far away, it is causally disconnected. Signals from there cannot reach us, no matter how sensitive our instruments become. This leads to an uncomfortable but honest realization. Some questions about black holes may not have answers in the traditional sense, or rather, they may have answers that cannot be verified. Still, physicists are not content to stop asking. Because black holes sit at the crossroads of the two most successful theories we have ever built: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of matter and energy at the smallest scales. Inside black holes, these two frameworks collide, and neither fully survives the encounter. That collision produces paradoxes, and paradoxes are not failures of science, they are signposts. They tell us where our understanding is incomplete. One of the most famous of these is the question of information. In everyday life, information is never truly destroyed. If you burn a book, the words don't vanish completely. They are scrambled into ash, smoke, and heat. In principle, the information still exists, just dispersed. Quantum physics insists that this must always be true. Information cannot be erased from the universe. Black holes appear to challenge that rule. When something falls into a black hole, all the details that describe it, its structure, composition, history, seem to disappear beyond the event horizon. If the black hole later evaporates, as some theories predict, where does that information go? Is it lost forever? If so, quantum theory breaks. If not, how is it preserved? Questions like this are why black holes are more than just exotic cosmic objects. They are pressure tests for our deepest ideas about reality. And yet, it's important to keep one thing firmly in mind as we explore these ideas. Not every proposed answer carries the same weight. Some are solidly grounded in observation and theory. Others are speculative, imaginative, and untested. Science does not treat all possibilities equally, even when it allows room for bold thinking. When people ask whether black holes are gateways to other universes, portals to new regions of space-time, or tunnels through reality itself, they are often blending serious theoretical ideas with science fiction interpretations. The truth usually sits somewhere quieter and more nuanced. The goal of this article is not to feed mystery for its own sake, nor to dismiss wonder. It is to walk carefully along the line between what we know, what we strongly suspect, and what remains open, and to do so without unnecessary jargon or exaggeration. We will explore what black holes are, how they form, what happens near them, what physics predicts about their interiors, and why the idea of the other side may be misleading from the start. Along the way, we will use analogies drawn from everyday life, not to oversimplify, but to anchor abstract ideas in something familiar. By the end, the answer to what's on the other side of a black hole may feel less like a destination and more like a mirror, reflecting the limits of our theories, the boundaries of observation, and the humility built into scientific inquiry itself. And that, perhaps, is what makes black holes so compelling, not because they promise secret worlds hidden behind cosmic curtains, but because they reveal just how much remains unfinished in our understanding of the universe. To understand what might exist on the other side of a black hole, we first need to clear away a surprising amount of misunderstanding about what a black hole actually is. Not the cinematic version, not the pop science shorthand. The real thing as far as physics can currently describe it. A black hole is not a hole in space. Nothing is missing where a black hole sits. There is no tear, tunnel, or puncture in the fabric of the universe. Instead, a black hole is a region of space where matter has been compressed so tightly that the gravity overwhelms every other force we know how to measure. A useful analogy is to imagine placing weights on a trampoline. A tennis ball creates a small dip. A bowling ball creates a deeper one. If you keep adding mass, the fabric stretches further and further. A black hole is what happens when the trampoline analogy breaks down entirely. The dip becomes so steep that anything rolling nearby inevitably slides inward, and once it crosses a certain boundary, it can no longer climb back out. That boundary is called the event horizon. The event horizon is not a physical surface. There is no shell, wall, or glowing edge. You wouldn't bump into it. If you were falling toward a sufficiently large black hole, you wouldn't feel anything special at the moment you crossed it. No alarm would go off. No sudden force would hit you. From your perspective, physics would appear to continue as usual. From the outside, however, something very different happens. To a distant observer, objects falling toward a black hole appear to slow down as they approach the event horizon. Their clocks tick more slowly. Their light becomes increasingly redshifted, stretched to longer and longer wavelengths. Eventually, that light fades from view entirely. The object never quite seems to cross the horizon. It just becomes dimmer, slower, and more distorted until it effectively disappears. This is not an illusion or a camera problem. It's a consequence of how space-time behaves in extreme gravity. Time itself flows differently depending on how deep you are in a gravitational field. This effect has been measured directly near Earth using atomic clocks on satellites. Near a black hole, the same effect becomes dramatic. This dual perspective, normal from the inside, frozen from the outside, already hints at why asking, "What's on the other side?" is so tricky. There is no single, universal frame of reference that tells the full story. Now, let's talk about what lies beneath the event horizon, according to our current theories. In classical general relativity, once something crosses the event horizon, it inevitably moves toward the singularity. The singularity is not a place in the ordinary sense. It is a mathematical outcome where density becomes infinite, and space-time curvature becomes infinite as well. That word, infinite, is a warning sign. In physics, infinities usually mean the theory is being pushed beyond its domain of validity. They are not treated as literal descriptions of reality. For example, classical physics predicts infinite energy at a point charge, but quantum theory replaces that with a more accurate description. Similarly, the singularity likely represents a failure of general relativity, rather than a true physical object. Still, according to the equations, everything inside the event horizon is forced toward this central region. Not because it's being pulled in the usual sense, but because space-time itself is shaped in such a way that moving inward is as unavoidable as moving forward in time. This brings up an important idea. Inside a black hole, inward becomes like future. Outside a black hole, you can choose to walk north or south, forward or backward. Inside the event horizon, all possible paths point toward the singularity. Just as you cannot choose to stop moving into the future, you cannot choose a path that avoids the center. This is deeply counterintuitive, but it's not mystical. It's geometry. Another misconception worth clearing up is the idea that black holes constantly grow by swallowing everything nearby. In reality, most black holes are remarkably quiet. They only grow when matter falls into them, and in most regions of space, matter is sparse. The black hole at the center of our galaxy, Sagittarius A, is currently consuming very little material. When black holes do feed actively, they don't do so invisibly. Matter spiraling in heats up, glows intensely, and releases enormous amounts of energy before crossing the event horizon. In fact, some of the brightest objects in the universe are powered not by stars, but by matter falling toward black holes. So, if black holes are not cosmic vacuum cleaners, not literal holes, and not necessarily violent destroyers, what exactly makes them so mysterious? The answer is information. In everyday experience, when something changes form, the information about it is preserved in principle. Smash a glass, and you could, with enough patience, reconstruct its original shape by tracking every fragment and every vibration. Physics assumes this principle holds universally. Black holes appear to violate it. When information crosses the event horizon, it becomes inaccessible. If the black hole later evaporates through a process called Hawking radiation, which we'll explore in detail later, what happens to that information? Is it encoded in the radiation? Is it destroyed? Is it hidden somewhere inaccessible? This question is known as the black hole information paradox, and it has occupied some of the brightest minds in physics for decades. It is not a philosophical curiosity. It is a direct clash between quantum mechanics and general relativity. This is where speculative ideas begin to emerge. Not because physicists enjoy wild theories, but because the existing frameworks don't fully agree. Some proposals suggest that information is stored on the event horizon itself, spread out like a hologram. Others suggest it escapes slowly through quantum effects. Still, others propose more radical ideas involving new dimensions or changes to space-time itself. And yes, some theories suggest that black holes might connect to other regions of space-time. But these ideas are far more constrained and subtle than popular depictions imply. Before we can assess those possibilities, we need to build a stronger foundation. We need to understand how black holes form, what types exist, and how real observations constrain our imagination. Only then can we responsibly ask whether there truly is an other side. And if so, what that phrase could even mean in a universe governed by relativistic spacetime and quantum uncertainty. That's where we're headed next. To understand what might exist beyond a black hole's event horizon, we also need to understand how black holes come into existence in the first place. Their origins matter more than it might seem, because the way something forms often determines what rules it must obey afterward. A puddle forms differently than a glacier. A campfire behaves differently than a star. Black holes are no exception. The simplest way to think about a black hole's birth is as a failure of balance. Stars are delicate negotiations between opposing forces. Gravity constantly tries to pull everything inward, compressing the star. At the same time, nuclear fusion in the star's core pushes outward, generating heat and pressure that resist collapse. For most of a star's life, these forces reach an uneasy truce. Gravity squeezes. Fusion pushes back. The star holds its shape. But that balance does not last forever. When a massive star runs out of fuel, fusion slows and eventually stops. The outward pressure weakens. Gravity, patient and relentless, finally wins. The star collapses under its own weight. In some cases, the collapse halts, producing a neutron star, an object so dense that a teaspoon of its material would outweigh a mountain. But if the star is massive enough, even neutron pressure cannot stop the collapse. That's when a black hole is born. The key point here is that a black hole forms from ordinary matter, governed by the same physical laws that apply everywhere else. There is no exotic substance required, no special conditions beyond mass and gravity. Black holes are not foreign intrusions into the universe. They are natural outcomes of stellar evolution. This already tells us something important. Whatever lies inside a black hole must arise from the same universe we already inhabit. It is not imported from elsewhere. If there is an other side, it emerges from known physics pushed to an extreme, not from a separate realm stitched on afterward. There are several types of black holes, and each tells a slightly different story. The smallest known category is stellar mass black holes, formed from collapsing stars. These typically range from a few times the mass of the Sun to a few dozen times its mass. They are scattered throughout galaxies, including our own, quietly orbiting among stars. At the other extreme are supermassive black holes, found at the centers of galaxies. These giants can be millions or even billions of times more massive than the Sun. The one at the center of the Milky Way weighs about 4 million solar masses. Others, in distant galaxies, dwarf even that. How these supermassive black holes formed is still an active area of research. Some may have grown from smaller black holes over time, merging and feeding on surrounding matter. Others may have formed very early in the universe's history from massive clouds of gas collapsing directly. Either way, they appear to be deeply connected to galaxy formation itself. This matters because the internal structure of a black hole, as predicted by theory, depends on its mass and history. Larger black holes have gentler tidal forces at their event horizons. Smaller ones are more violent. This leads to an unintuitive result. Falling into a supermassive black hole could be less immediately destructive than falling into a smaller one. To put it another way, the most dangerous black holes are not the biggest ones. They are the compact ones. This brings us to a concept often exaggerated in popular explanations: spaghettification. Spaghettification refers to the stretching effect caused by extreme differences in gravitational pull across an object. If your feet are closer to a black hole than your head, gravity pulls harder on your feet. The result is stretching along one axis and compression along another. It's real physics, not just a colorful metaphor. But the severity of this effect depends on how quickly gravity changes with distance. Near a small black hole, that change is abrupt. Near a supermassive black hole, it's more gradual. In principle, you could cross the event horizon of a supermassive black hole without noticing anything unusual at that moment. This fact alone complicates the idea of a dramatic boundary separating our universe from whatever lies beyond. If crossing the event horizon does not feel special locally, then the idea of an obvious transition to another realm becomes less plausible. The boundary is real, but it's not experiential. Another crucial concept to understand is causality. Physics is deeply concerned with cause and effect. One event leads to another. Signals propagate at finite speeds. The speed of light is the ultimate limit. Black holes introduce a region where causality behaves in a one-way fashion. Outside the event horizon, events can influence one another in multiple directions. Inside, all future-directed paths lead inward. This is not a metaphor. It's a statement about space-time geometry. Once you cross the event horizon, no action you take can influence the outside universe. This is not because you're blocked by a force field, but because the structure of space-time itself prevents outward influence. Asking what's on the other side is therefore not like asking what's beyond a wall. It's more like asking what happens after a point of no return in time. This distinction is subtle but critical. If you ask what happens beyond tomorrow, you are not asking about a place. You are asking about a future state. Inside a black hole, inside behaves similarly. It is not a region you can exit, just as you cannot exit the future. This also explains why black holes are not portals in the usual science fiction sense. A portal implies two-way travel, or at least the possibility of return. Black holes do not allow that under classical physics. Now, let's address a common question. Could black holes lead somewhere else, even if we can't come back? Some solutions to Einstein's equations suggest mathematical structures called wormholes, which connect distant regions of space-time. These solutions are elegant and intriguing. They look, on paper, like tunnels through space-time. But there's a catch. The wormholes that arise naturally in general relativity are unstable. They collapse too quickly for anything, even light, to pass through. Keeping them open would require exotic forms of matter with negative energy density, something we have never observed in nature. So, while wormholes are fascinating theoretical tools, there's currently no evidence that real black holes contain traversable tunnels to elsewhere. This doesn't mean the interior is boring. Far from it. As we approach the singularity in theoretical models, time and space swap roles in strange ways. Paths that once pointed outward become impossible. The concept of location itself becomes ambiguous, and eventually the equations stop making sense altogether. This is where quantum gravity, a theory we do not yet possess, would be required to continue the story. Until such a theory exists, any description of the deep interior remains speculative. And yet, speculation does not mean guesswork. Physicists use constraints, consistency, and known principles to explore possibilities. They test ideas against observations, even when those observations are indirect. One of the most important of these constraints comes from black hole thermodynamics. Black holes behave like thermodynamic objects. They have temperature. They have entropy. They obey laws that closely resemble the laws of heat and energy. This was not expected. It emerged gradually through careful theoretical work. Entropy, in particular, is revealing. A black hole's entropy is proportional not to its volume, but to the area of its event horizon. This strange result suggests that information about what falls in may be encoded on the boundary rather than in the interior. This idea, known broadly as the holographic principle, hints that the universe may be describable in fewer dimensions than it appears. It does not say black holes are holograms in the everyday sense, but it suggests that information behaves in ways we don't yet fully understand. If information is preserved at the horizon, then perhaps there is no need for an other side in the traditional sense. Perhaps the interior is not a place where information goes, but a transformation of how information is represented. This is one of the deepest shifts in thinking that black holes force upon us. They may not hide secret worlds. They may instead reveal that our intuition about space itself is incomplete. In the next part, we'll confront one of the most persistent ideas head-on: whether black holes could open into new universes, baby universes, or disconnected regions of reality, and why physicists approach those ideas with both curiosity and caution. Once black holes enter the conversation, the idea of other universes almost always follows. It feels natural. If space-time can bend, twist, and collapse, then maybe it can also connect. Maybe falling into a black hole doesn't end the story, but redirects it. Maybe the interior opens into something new. Physicists didn't invent this idea because it sounded exciting. They encountered it because the mathematics kept pointing in that direction, even when they tried to avoid it. In Einstein's equations, certain solutions describe structures that look like bridges in space-time. These are commonly called wormholes, though the technical term is an Einstein-Rosen bridge. In the simplest version, the equations suggest that a black hole might be connected to another region of space-time through a tunnel-like structure. At first glance, this sounds exactly like a gateway, a cosmic shortcut, an entrance on one side, an exit somewhere else. But physics is rarely that generous. When researchers studied these solutions more closely, they discovered a problem. The bridges collapse too quickly, faster than anything could pass through them. Even light wouldn't make it. The wormhole pinches off almost instantly, leaving no usable passage. An analogy helps here. Imagine two rooms connected by a door that opens and slams shut faster than any object can move. Technically, the connection exists for a moment. Practically, it's useless. To make a wormhole stay open, the equations require something exotic: negative energy density. This isn't just very low energy. It's energy that behaves in ways opposite to normal matter. Gravity pushes instead of pulls. Space stretches instead of contracts. We know negative energy can exist in tiny amounts due to quantum effects, such as the Casimir effect. But nothing remotely close to what would be needed to stabilize a wormhole has ever been observed. As far as we know, nature doesn't provide the materials required. This is why most physicists are careful when talking about black holes as gateways. The math allows the idea, but the physical requirements make it extraordinarily unlikely. Still, the story doesn't end there. Another idea emerges when we push black hole physics to its limits: baby universes. Some theoretical models suggest that when matter collapses into a black hole, the extreme conditions near the singularity might cause space-time to rebound rather than terminate. Instead of ending in a singular point, space-time could pinch off and expand into a new region entirely. A new universe disconnected from ours. In this picture, a black hole is not a door, but a seed. A collapsing region in one universe becomes an expanding region in another. From the outside, we see a black hole. On the inside, if such a concept even applies, something like a Big Bang might occur. This idea is speculative, but it's not arbitrary. It arises from attempts to merge general relativity with quantum mechanics. Quantum physics does not like infinities. When equations predict infinite density, quantum effects often intervene, smoothing things out. Think of it like zooming in on a coastline. From far away, it looks jagged and sharp. Up close, the sharp edges blur into grains of sand. Quantum gravity might play a similar role near black hole singularities. However, even if baby universes exist, they raise difficult questions. First, there's no known way for information to travel back. If a new universe forms, it would be causally disconnected from ours. No signals, no communication, no return. Second, there's no observational evidence. These ideas live entirely in the realm of theory. They are mathematically interesting, but they make no testable predictions we can currently check. Third, they don't solve the information problem by default. Creating a new universe doesn't automatically explain how information is preserved or where it goes. Because of these issues, most physicists treat baby universe ideas as intriguing possibilities, rather than established explanations. Another popular concept is the multiverse, and black holes are often pulled into that discussion. The multiverse is not one theory. It's a family of ideas. Some versions arise from cosmic inflation, where different regions of space expand at different rates. Others come from string theory, which allows many possible configurations of physical laws. In some multiverse models, black holes might act as connections between regions or as generators of new universes with slightly different physical constants. This idea is sometimes called cosmic natural selection, where universes that produce more black holes also produce more offspring universes. It's a clever analogy, but again, evidence is the problem. The multiverse remains speculative because it sits beyond observational reach. Black holes do not give us a backdoor into other universes, at least not in any way we can verify. This brings us to an important principle in science. explanatory restraint. Physicists are not opposed to bold ideas, but bold ideas must eventually answer to data. When multiple explanations exist, the simplest one consistent with known evidence is usually preferred. Right now, the simplest explanation for black holes is that they are extreme but internal features of our universe, not gateways to elsewhere. That doesn't mean the interior is trivial. Far from it. Another idea worth examining is the notion that black holes might not contain a traditional interior at all. Instead, everything that falls in could be encoded on the event horizon itself. This idea stems from the holographic principle mentioned earlier. A helpful analogy is compression. When you zip a large file on your computer, the information doesn't disappear. It's reorganized. The contents still exist, but in a different form. Similarly, information falling into a black hole might be compressed into a two-dimensional surface description on the horizon. If this is correct, then the question, what's on the other side, becomes misplaced. There is no deep interior storing information. The interior may be an emergent description, not a fundamental one. This idea gained support from studies of black hole entropy. The fact that entropy scales with surface area rather than volume is not something physicists expected. It suggests that our intuition about space may be misleading. The universe might not store information the way we think it does. All of this forces us to confront a possibility that feels uncomfortable but increasingly plausible. Black holes may not hide secret realms. They may instead expose the limitations of our mental models. We want space to behave like a container. We want boundaries to separate places. We want continuity. Black holes resist those assumptions. They are not doors. They are not walls. They are not tunnels. They are regions where space-time becomes so distorted that ordinary language stops working cleanly. In the next part, we'll tackle one of the most persistent and unsettling questions directly. What happens to information when a black hole evaporates, and why that question reshaped modern theoretical physics? The question of what lies on the other side of a black hole eventually runs into a deeper and more troubling problem, one that doesn't involve distant universes or hidden tunnels at all. It asks something much simpler and much harder to accept. What happens to information? In everyday life, information is stubborn. Burn a book, and the words aren't gone, just scrambled into smoke, ash, and heat. Smash a hard drive, and the data still exists in principle, hidden in the arrangement of atoms. Physics, at its core, assumes that information is never truly destroyed. It can change form, but it doesn't vanish. This idea is deeply built into quantum mechanics. The equations that describe particles demand reversibility. If you know the present perfectly, you can reconstruct the past. Information loss breaks that rule. Black holes appear to break it completely. When physicist Stephen Hawking studied black holes in the 1970s, he made a discovery that shocked the scientific world. Black holes, which were thought to only absorb matter and energy, should actually emit radiation. This radiation, now known as Hawking radiation, arises from quantum effects near the event horizon. Space is not empty. Even in a vacuum, particle-antiparticle pairs constantly pop into existence and annihilate each other almost instantly. Near the event horizon, this process can be disrupted. If one particle falls into the black hole while the other escapes, the escaping particle becomes real radiation. From the outside, it looks like the black hole is slowly leaking energy. Over extremely long timescales, far longer than the current age of the universe, this process causes black holes to shrink. Eventually, they evaporate completely. This is where the problem explodes. If a black hole forms from matter containing information, atoms, particles, quantum states, and later evaporates into featureless thermal radiation, where did that information go? Hawking initially concluded that it was simply lost. That answer caused a crisis. Information loss would mean that the universe is fundamentally unpredictable. Two identical states could evolve into different futures. The rules of quantum mechanics would be broken at the deepest level. Most physicists found this unacceptable. This tension became known as the black hole information paradox, and it dominated theoretical physics for decades. The debate wasn't philosophical, it was mathematical and foundational. Either black holes destroy information, or our understanding of gravity is incomplete. Several possibilities emerged. One idea was that information escapes with Hawking radiation, but in a highly scrambled form. The radiation looks random, but subtle correlations encode the original information. Like a shredded document that could, in theory, be reassembled if you had infinite patience and precision. Another idea was that information remains stored on the event horizon itself. This connects directly to the holographic principle. Instead of falling into an interior volume, information becomes imprinted on the black hole's surface. A third proposal suggested that information falls into a baby universe, leaving our universe but still existing somewhere else. This avoids destruction, but introduces untestable regions beyond observation. For years, no one could prove which, if any, of these ideas was correct. Then, something interesting happened. String theory, a framework originally developed for entirely different reasons, began to offer tools for calculating black hole entropy in specific cases. These calculations matched the expected entropy values exactly, suggesting that black holes do store information in a consistent way. Later, developments in quantum gravity and holography strengthened this picture. In particular, the ADS-CFT correspondence, a mathematical duality between gravity in a volume and quantum physics on its boundary, showed explicitly that information can be preserved even when gravity is involved. In these models, black holes behave like complex quantum systems whose information is never destroyed, only transformed. More recently, calculations involving quantum entanglement and spacetime geometry have shown that the process of black hole evaporation can be consistent with information preservation. These results don't yet apply to all realistic black holes, but they strongly suggest that Hawking's original conclusion was incomplete. Hawking himself eventually changed his mind. The consensus today is that information is not destroyed by black holes. It is encoded in subtle correlations and released over time through Hawking radiation. But this answer introduces a strange consequence. If information is preserved, then the black hole interior may not be an independent place where information resides. Instead, what we think of as the inside might be a useful illusion, an emergent description that only makes sense from certain perspectives. This leads to unsettling ideas like black hole complementarity, where different observers experience different but equally valid realities. To an outside observer, information never crosses the horizon. To a falling observer, nothing unusual happens at the horizon at all. Both descriptions are correct, but they cannot be combined into a single picture. In other words, asking what is on the other side of a black hole may be like asking where yesterday goes. It's a meaningful question locally, but globally misleading. Black holes don't just challenge our understanding of space, they challenge how reality itself is described. In the next part, we'll explore what actually happens to an object falling into a black hole, from tidal forces to time distortion, and why the experience depends entirely on who is watching. To understand what might be on the other side of a black hole, we first have to confront a more immediate and very human question. What would actually happen to you if you fell into one? This question sounds dramatic, but it turns out to be one of the most important tools physicists have for understanding black holes. Not because anyone expects to test it directly, but because the laws of physics should describe what happens to any object, observer included. Let's begin far away from the black hole, at a distance where space still behaves politely. From far away, a black hole looks surprisingly normal. It has mass, so it pulls on surrounding objects just like any star or planet. If the black hole has the mass of our Sun, you could orbit it exactly the same way you orbit the Sun now. Nothing strange would happen at that distance. No tearing, no stretching, no dramatic effects. The weirdness begins only when you get close. As you fall toward the black hole, gravity becomes stronger. But gravity isn't just about strength. It's about differences. One side of your body is slightly closer to the black hole than the other, and therefore pulled a little more strongly. This difference is called a tidal force. On Earth, tidal forces are mild. The moon pulls more strongly on the side of Earth facing it than on the far side, stretching the oceans and creating tides. You don't notice this effect on your body because the difference is tiny. Near a black hole, that difference becomes extreme. If you fall feet first toward a black hole, your feet are pulled much harder than your head. The result is a stretching force along your body and a squeezing force across it. Physicists call this process spaghettification, which is one of the rare times humor has officially entered serious physics vocabulary. In small black holes, this stretching happens far outside the event horizon. You would be torn apart long before crossing it. But supermassive black holes behave differently. At the center of most galaxies, including our own, sit black holes millions or billions of times more massive than the Sun. Their gravity near the horizon is actually gentler because the horizon is much larger. In that case, you could cross the event horizon without noticing anything unusual at that exact moment. No wall, no shock, no sudden darkness. The event horizon is not a physical surface. It's a boundary in space-time, a point of no return, not a place where something visibly happens. From your perspective, falling inward, everything feels normal. You continue drifting, floating, falling. You can still see stars behind you. Your heartbeat continues. Your thoughts remain intact. This is deeply unsettling, because from the outside, observers see something completely different. To a distant observer watching you fall, you never actually cross the event horizon. As you approach it, your motion appears to slow down. Your signals take longer to reach the outside universe. Your light becomes more redshifted, stretched to longer wavelengths. Eventually, you seem to freeze at the edge. From the outside, you fade away, becoming dimmer and redder until you disappear. From your own perspective, none of this happens. This is not an illusion or a trick of instruments. It is a real difference in how time flows for different observers. Near a black hole, time itself bends. According to Einstein's general relativity, gravity is not just a force, it is the curvature of space-time. Strong gravity slows time. The closer you are to a massive object, the slower your clock runs relative to someone farther away. At the event horizon, this effect becomes extreme. From the outside, time at the horizon effectively stops. From the inside, your own clock continues normally. This creates one of the most disturbing ideas in modern physics. There is no single, universal timeline that everyone agrees on. Different observers experience different realities, and both are correct. This leads to the concept known as black hole complementarity. The idea is that no observer ever sees a violation of physical laws, but no observer can see the entire story either. The outside observer sees you asymptotically approach the horizon, never crossing it, while your information is somehow encoded on the horizon itself. You, the falling observer, cross the horizon smoothly and continue inward, unaware of anything special happening at that boundary. These two descriptions contradict each other, but they can never be directly compared. You cannot send information back out once you cross the horizon. The outside observer cannot see inside. Reality, in this sense, depends on perspective. This isn't just philosophical. It matters deeply for the question of what exists on the other side. Because if the interior of the black hole depends on the observer, then the other side might not be a single objective place. As you continue falling inward, tidal forces eventually become overwhelming, even in a supermassive black hole. Your body stretches, then atoms stretch, then nuclei. Then spacetime itself becomes violently distorted. All paths through spacetime lead inward. No direction points outward anymore, just as in ordinary space all directions on Earth's surface eventually lead south if you go far enough. At this stage, according to classical general relativity, you approach the singularity. The singularity is not a point in space. It is a moment in time, a future endpoint. In the equations, density becomes infinite. Curvature becomes infinite. Time ends. But physicists are almost certain this description is incomplete. Infinity in physics is usually a sign that a theory has broken down. General relativity does not include quantum mechanics, and near the singularity, quantum effects should dominate. We don't yet have a full theory of quantum gravity, but we have hints. Some approaches suggest that the singularity is replaced by a highly compressed but finite state. Others suggest spacetime undergoes a transition, perhaps a bounce, or a phase change. In some speculative models, falling into a black hole could lead to a region where spacetime reconnects in a different way, potentially forming something like a new expanding universe. This idea often appears under the label black hole cosmology. In these models, black holes are not dead ends but seeds. each black hole could give rise to a new universe, disconnected from ours. From inside, that new region might look like a Big Bang. From outside, nothing unusual happens beyond mass loss through Hawking radiation. This idea remains speculative, but it is mathematically consistent in some frameworks. What's important is this. Modern physics no longer confidently says that the interior of a black hole is simply a meaningless point of destruction. Instead, it appears to be a boundary between descriptions, between classical space-time and something deeper. So, when we ask what is on the other side of a black hole, the most honest answer may be this. There may be no single other side that everyone agrees on. There may be only different stories told by different observers, each internally consistent, each incomplete, and each revealing something true. In the next chunk, we'll push this idea further and ask whether black holes connect to other regions of space-time. Wormholes, Einstein-Rosen bridges, and whether such connections could ever be real, stable, or observable. If the inside of a black hole is not simply a dead end, then the next natural question becomes almost unavoidable. Could it connect to somewhere else? This idea is older than many people realize. In fact, it appeared almost immediately after Einstein's equations were first solved for black holes. When physicists examined the mathematics carefully, they noticed something strange hiding inside the solutions. The equations did not just describe a collapsing region of space-time. They also allowed for a kind of bridge. This bridge is what we now call a wormhole. The original version appeared in 1935, when Albert Einstein and Nathan Rosen explored the geometry of black holes. They found that, mathematically, the space-time around a black hole could be extended to include a second region, connected through a narrow throat. This structure became known as an Einstein-Rosen bridge. In very loose terms, it looked like a tunnel linking two separate parts of space-time. Popular culture later ran with this idea. Wormholes became shortcuts through space, portals between galaxies, or even doors to other universes. But the physics is much less forgiving than the stories. The first problem is stability. The Einstein-Rosen bridge exists only fleetingly. In the equations, it pinches off so quickly that nothing can actually pass through it. Any attempt to enter collapses the tunnel before crossing. Imagine trying to run through a door that slams shut faster than light can cross the doorway. That is the practical reality of this early wormhole model. To make a traversable wormhole, one that stays open long enough for matter or information to pass through, you need something exotic. Specifically, you need negative energy. In everyday experience, energy is always positive. Mass has energy. Light has energy. Motion has energy. Everything adds to the total. But in quantum physics, things get weird. Under certain conditions, quantum fields can exhibit regions of negative energy density. This does not mean energy is less than nothing in a philosophical sense. It means that compared to the surrounding vacuum, the energy is lower. The Casimir effect is a famous example. Place two metal plates extremely close together in a vacuum, and the quantum fluctuations between them are reduced compared to outside. This creates a tiny negative energy region. In theory, enough negative energy could counteract gravity's tendency to collapse a wormhole, holding it open. In practice, the amount required is astronomical. we are talking about quantities far beyond anything we know how to produce or control. Even if the universe allows such structures, they may be effectively impossible to engineer. But nature does not always care about what is convenient. Some modern theories suggest that black holes and wormholes might be deeply connected at a fundamental level. One particularly intriguing idea is called ER/EPR. The name sounds cryptic, but the concept is surprisingly elegant. ER refers to Einstein-Rosen bridges. EPR refers to Einstein-Podolsky-Rosen entanglement, quantum entanglement. Quantum entanglement occurs when two particles become linked in such a way that measuring one instantly affects the state of the other, no matter how far apart they are. Einstein famously disliked this, calling it spooky action at a distance. But experiments have confirmed that entanglement is real. The EPR conjecture proposes that entangled particles are connected by microscopic wormholes, not traversable tunnels, but geometric connections in spacetime itself. In this view, spacetime is not fundamental. It emerges from quantum entanglement. If this idea is correct, then wormholes are not rare, exotic structures. They are everywhere, on tiny scales, stitching spacetime together. Black holes, which are deeply entangled objects, could then be connected to other regions in subtle, non-classical ways. This does not mean you could jump into a black hole and come out somewhere else like a sci-fi hero. But it suggests that the interior of a black hole may be encoded in correlations with the outside universe. This brings us back to information. One of the biggest puzzles in black hole physics is the information paradox. According to quantum mechanics, information is never destroyed. The exact state of a system must always be recoverable, at least in principle. But classical black holes seem to destroy information. Anything that falls in disappears behind the horizon and is lost forever. Stephen Hawking complicated this further when he discovered that black holes are not completely black. Due to quantum effects near the event horizon, black holes emit radiation, now called Hawking radiation. Over immense timescales, they evaporate. This creates a problem. If a black hole evaporates completely, where does the information go? If it is destroyed, quantum mechanics breaks. If it escapes, how? Modern physics strongly suggests that information is preserved. The radiation must somehow carry it out. This implies that the event horizon is not an empty boundary. It has structure. It stores information. One proposal is that all the information about what falls in is encoded on the horizon itself, like a hologram. This is known as the holographic principle. Just as a two-dimensional hologram can encode a three-dimensional image, a two-dimensional surface in space-time can encode the physics of a three-dimensional volume. In this picture, the interior of the black hole is not an independent region. It is a different way of describing information stored on the surface. This again challenges the idea of a literal other side. The black hole interior may be more like a reinterpretation of data than a place you could visit. Yet some physicists argue that the interior must still be real in some sense, because falling observers experience it. This tension has led to some extreme ideas. One of them is the firewall hypothesis. According to this idea, the smooth event horizon described by general relativity cannot exist if information is preserved. Instead, the horizon becomes a violent region filled with high-energy particles. anyone falling in would be instantly destroyed. This solves the information problem, but violates the equivalence principle, the idea that falling freely should feel like floating in empty space. Most physicists are unhappy with this outcome. Another possibility is that space-time itself rearranges in subtle ways, allowing information to escape without drama. In some models, the interior of the black hole is not destroyed, but gradually leaks information through correlations with Hawking radiation. In others, the black hole interior becomes disconnected as the black hole evaporates, leaving no singularity behind. All of these ideas share a common theme. Black holes force us to confront the limits of our theories. They sit at the intersection of gravity, quantum mechanics, thermodynamics, and information theory. When we ask what is on the other side of a black hole, we are really asking which of our assumptions about reality still hold under extreme conditions. Is space-time fundamental or emergent? Is locality absolute or approximate? Is information tied to space, or can it exist without it? So far, every attempt to answer these questions has revealed that our everyday intuitions are deeply misleading. Black holes are not just cosmic vacuum cleaners or one-way traps. They are laboratories for the deepest questions in physics. In the final part, we'll step back and ask the most important question of all. Even if there is something on the other side of a black hole, will we ever be able to know it? At some point, every scientific investigation runs into a boundary that is not made of matter or energy, but of knowledge itself. Black holes represent one of the clearest examples of this kind of limit. They are not just distant or difficult to study. They are structured in such a way that certain information may be fundamentally inaccessible to outside observers. This does not mean physics gives up, but it does mean physics must be honest about what questions can be answered experimentally, and which ones may remain theoretical for a very long time. The event horizon is the key obstacle. Once something crosses it, no signal can return. No light, no particles, no encoded message. From the outside, that region is causally disconnected forever. This is not a technological limitation. It is built into the structure of space-time as described by relativity. Because of this, we will likely never directly observe what happens beyond the horizon. That realization can feel unsatisfying. Science is built on measurement, testing, and verification. If something cannot be observed, how can it be considered real? But physics has faced this problem before. We cannot directly observe the inside of an atom with our eyes, yet atomic theory works because its predictions match experiments. We cannot directly see space-time curvature, but we observe its effects through gravity and gravitational waves. Similarly, black hole interiors may never be directly observed, but they still influence physics through consistency requirements. Theories that describe them must agree with everything we can measure outside. This is where indirect evidence becomes crucial. Gravitational waves detected by observatories like LIGO and Virgo have already transformed black holes from abstract solutions into measurable objects. When two black holes merge, they send ripples through space-time that carry information about their masses, spins, and horizons. Future detectors may be able to probe even subtler features. There is active research into whether echoes in gravitational wave signals could reveal deviations from classical horizons. If the interior structure is different from general relativity's predictions, it might leave faint fingerprints in the ring-down phase after a merger. So far, observations match Einstein's equations remarkably well. That does not rule out exotic interiors, but it constrains them. Astronomers are also studying black hole shadows, such as the images of the supermassive black holes in M87 and our own Milky Way. These images do not show the horizon itself, but the silhouette created by light bending around it. The size and shape of that shadow depend on space-time geometry near the horizon. Any dramatic departure from standard physics would likely show up there. Again, the results so far align with general relativity. This does not mean there is nothing interesting inside black holes. It means that whatever is happening must be subtle enough to preserve the external behavior we observe. In a sense, black holes are extremely well behaved from the outside, even if they are wild on the inside. This brings us to a deeper point. Black holes challenge not just physics, but how we think about explanation. When people ask, "What's on the other side of a black hole?" they often imagine a location, a place you could point to, a region of space. But black holes may not cooperate with that intuition. The interior might not be a place in the usual sense. It might be a process, a transformation, a reorganization of information. In some approaches to quantum gravity, space-time itself is not fundamental. It emerges from deeper mathematical relationships. In that case, asking what is inside a black hole might be like asking what is inside a computation. There is no single answer. It depends on how the information is being represented. This is unsettling, but also exciting. It suggests that black holes are not just objects within the universe. They are probes of the universe's underlying structure. They force us to confront the relationship between geometry and information, between time and entropy, between reality and description. They also raise philosophical questions that science cannot fully avoid. If information is preserved, but scrambled beyond practical recovery, is it meaningfully preserved? If the interior of a black hole exists only as correlations encoded elsewhere, is that existence different from ours? If space-time can tear, reconnect, or emerge from entanglement, what does that say about causality? These are not just abstract musings. They influence how physicists build theories and decide what counts as an explanation. Importantly, black holes also remind us that science progresses by narrowing uncertainty, not eliminating mystery. The goal is not to make the universe boring or predictable. It is to understand where our knowledge ends and why. In that sense, black holes are honest objects. They tell us plainly there are limits, and yet those limits are productive. The effort to understand black holes has led to breakthroughs in thermodynamics, quantum theory, information science, and mathematics. Concepts like entropy, holography, and entanglement have become central across physics because of black holes. Even if we never know exactly what lies beyond the horizon, the attempt to answer the question reshapes everything else. There is also a human dimension to this. Black holes capture our imagination because they combine familiarity and alienness. They are predicted by equations written on chalkboards, yet they behave in ways that defy common sense. They exist in our universe, but they point beyond it. In a way, They mirror our own position as observers. We are inside the universe, trying to understand the universe, using tools that evolved for survival on a small planet. Black holes remind us that reality is under no obligation to be intuitive. And that is not a failure of science. It is its strength. Science does not promise comforting answers. It promises reliable ones, constrained by evidence and logic. So, what is on the other side of a black hole? The most honest answer, for now, is this: we do not know. It could be a region of space-time that ends in a singularity. It could be a transformation into radiation over time. It could be a connection to another region, another universe, or another description entirely. It could be something we do not yet have the language to describe. What we do know is that black holes are not voids of ignorance. They are dense with meaning. They sit at the crossroads of our best theories, revealing their strengths and weaknesses. They tell us that space and time are flexible, information is fundamental, and intuition is optional. And, perhaps most importantly, they show us that even in a universe governed by precise laws, there is still room for profound uncertainty. That uncertainty is not an invitation to stop asking questions. It is an invitation to ask better ones. And as long as black holes exist, quietly shaping galaxies, merging in distant darkness, bending space-time without drama, they will continue to challenge us to rethink what reality actually is. Not from the other side, perhaps, but from the edge where knowledge meets the unknown.